Well, I might kick it off with a question, but I actually want to try and have as much interaction with the audience in this panel. We've got some time. A number of questions I have here kind of have been answered through the presentations, and I don't want to repeat those. One thing that I am interested in, though, is, well, actually, I'll have two questions. I'd like to hear from each of you what you consider to be the single most important barrier to making more rapid progress on low methane genetics as an approach, and how to overcome that barrier. Like, just if you had to pick one, what's the biggest thing? How do we fix it? Anyone can jump in and react, and even Alex, who's not a geneticist, happy to. But go Francisco. Yeah, please. Maybe just turn on the up. Yep.
Now, yes. I'm a geneticist, so I can be biased, but the most important thing is phenotyping. As you can imagine, measure methane emissions, it's hard and expensive. We are lucky because we are in the genomics era. So genomics is a beautiful tool that we have to improve traits that are hard and difficult to measure. But at the end of the day, we still need to develop a reference population where we need to phenotype the traits that we want to improve.
Anyone?
Well, I'll say as a non-geneticist, my biggest concern is two things. First, even if you are successful, you are going to make about 10% difference improvement in methane emissions. And second one is selecting against production, traits, or digestibility. So this is my biggest concerns.
Yeah, I think the phenotyping thing is absolutely true, and not just in the immediate term to get pilot genetic predictions for methane out, but how do you sustain this? We're constantly having to remind producers in sort of my extension role that we can't stop collecting phenotypes once a genomic evaluation gets released. If we stopped collecting phenotypes, as soon as we had that prediction, those would erode over the course of 5 or 10 years, right? They'd be not useful at all. So how do we continue to sustain this phenotypic collection? And I think the use of proxy phenotypes, whether that's through some sort of novel omics technology, through MIR in the context of dairy, or some other indicators that we're able to glean, that's what's going to help power this, but we're still going to need those gold standard phenotypes collected so that our populations stay up to date with all the genetics that have evolved over the course of time.
And Paul?
Yeah, I mean, it's collecting the data and continuing to collect the data and the cost of that data for sure. Like, I think that's what we're all kind of agreeing on.
Yeah, sorry to sound like a broken record. I thought it was interesting, that figure that I think Troy had showing phenotypes, and as you move to the right, the expense increases. And Troy, you didn't even have indirect calorimetry on there, and we're literally collecting shitloads of sample, collecting all of the feces and all of the urine, which takes tremendous amount of labor, and we appreciate the students for doing that. But the wonderful thing about some of these projects and the communication that's happening, I know Mike Vanderhaar, that's on Francisco's project, he called me out and he said, Paul, you really should be collecting samples and do spectral analysis on it. And so I think there'll be some opportunities to use some of these eloquent technologies in replace of the blunt force trauma that some of us have been doing.
Thank you. Alex, you said 10% might be out. I might want to just pry here a bit and see what people and how people might interact, but I guess I'd love to know what makes you come up with 10% being the maximum, and do you think that your legitimate questions about selecting against other desirable characteristics can be mitigated in a straightforward manner, assuring that the phenotyping that is done is capturing the right information, so you are not inadvertently selecting down a dead end? I mean, do you think it's an unmitigated problem, or it's just we have to be careful?
Well, to your first question, the 10% come from your neck of the woods, the sheep data.
10% so far, right? Yeah.
10% so far. The second question is a lot more difficult, and I don't think we have data to confirm any of that. But we know methane is coming from digested organic matter. So, decreasing digestibility is definitely going to decrease methane. And how is that related to the selection of these animals? I have still difficult times understanding it. We know passage rate, for example, is related to digestibility, and it is related also to methane emissions. So are we selecting for increased passage rate, decreased digestibility at the end of the day, or we are not? So I don't have an answer to this, but I think this should be a concern for everyone, and we should study it.
Any other observations on that? Or Francisco?
There you go. So, couple of things. As I mentioned before, right? The dairy cow today, she produces more than twice as much milk of a cow of 60 years ago. And 60% of that change is due to genetic selection. Now, the heritability for production traits are around 20%. And methane emission traits are at least as heritable as production traits. Our data is showing that they have heritabilities around 20-25%. Polls show even more variation today. So we strongly believe we can reduce methane emissions using selective breeding. The second one is, Alex is right, we have to be careful with the other traits. Now, there are farmers do not select for a single trait. And if they do, they're doing a mistake because there are multiple traits that are important. And that's why we use economic selection index. That is the best selection tool that we have. So at the end of the day, we will need to incorporate the methane emission trait in our economic selection index that will consider heritabilities and genetic correlation with other traits, and in that way we will move forward not only methane emissions but also the other traits.
Thank you. Another question is, each of you referred to projects you have funded from various sources, some may be federal, US federal NIFA or other grants, or initiatives like Greener Cattle, in your case, Francisco. And each is sort of intending to or is already collecting like good-sized data sets, let's say. Wouldn't say massive, right? But there are limits to how much money can get. But a few thousands. I guess I'm not a geneticist either, but I know it's like a big numbers game. So, like, how can we more effectively collaborate? Like, you're collecting your data and doing it in a certain way. You're doing phenotyping of a number of things, maybe not exactly the same as others. Like, how can we best create the conditions for the data to be pooled, shared, and everyone benefit from that? How do you create the incentives for people to want to be in there and willfully share that information they have, whether they be public sector, private sector, and benefit from that in the public good without having free riders? Like, how, just insights into sort of how to construct that, and maybe some ideas would be really interesting to hear from people. And anyone who wishes to jump in. Or have you already thought about that in the case of your own projects, of connecting to others and the Commodity Partnerships Program, for example, who may be also doing phenotyping? Are there opportunities that we can find ways to maximize?
So just from talking today, I've already figured out, there's a few people that I need to be talking to for collaboration of, we're using the same equipment, so what is the protocols that you're using? So for our particular project, I forgot to mention that it's a collaboration with industry and private producers. One of our producers is already collecting the data, and we're getting feedback from them of, okay, this is what you need to watch for when you're collecting your own data when we start down in South Texas. And then the questions about the microbiome, like, we didn't even consider that when we started setting up our phenotyping and trying to figure out how do we incorporate that now, because it is such a big issue. And so then listening to Troy going, oh, that's easy, I can do that. That's something that now I can give him those numbers from our cattle that'll beef up his project, and at the same time benefit the community as well. So I think it's just communicating that this is all the projects that we have going on. This is the similar equipment that we're using. How can we cross-communicate? Because when in genetics, numbers is king, right? Like phenotyping is king, but having high numbers, that's how we get our statistical power to say, yes, this is what it's doing.
Yeah, if I can just add to that a little bit, it's going to take data infrastructure too. Shuttling Excel files around probably not going to cut it, especially when we get to the level of doing this population-wide. So we need data infrastructure. I think that generally we're interested in working together as academics. You have a bunch of academics on the stage today. But the next question, I think about the beef industry, a little bit less coordinated in the genetic evaluation space, a handful of breeds that are all sort of jockeying for position and competitive advantage, whereas all the dairy genetic evaluation happens through the CDCB, which is a great resource. So trying to walk that line between how do we help all of the breeds collect data, integrate their data, leverage each other's data to develop a better tool at the end of the day, but not get their sort of heckles up about a competitive advantage going to their direct competitor for market share. So that's going to be something that takes some collaborations across academic institutions and with our nonprofit partners at breed associations in the beef sector anyway.
Anyone else have any thoughts?
You know, so I was talking to our team the other day, and I said, this is really an exciting time. I don't think there'll ever be another time in our career we're gonna have so many people in the world working on a single problem, and I think this meeting is a good example of that. But I do think, you know, your question is really important because there currently is no system to bring us all together. So I think that's a problem for all of us walking out the door, and we should figure that out. You know, different communities of geneticists and microbiologists have been pretty good at sharing data, uploading data, making it available. If I'm speaking critically about nutritionists, we've been less so. And so I think those are things that we need to figure out as we're walking out this door. The other thing is, I think you used the term freeloaders or something. I think we just have to make the data available, and there's no protection, and we just let it go. And some of these freeloaders will find out some really impactful things. So I think we just can't have the mindset of being protective of our data.
I guess that's just a reflection too with Amable's presentation earlier. You know, 81% of livestock methane emitted in low and middle income countries, and we know that the kind of work that's being discussed here is not routinely happening in those countries. So there's also a big effort we have to make to extend this approach more globally. I've got another question, quite a specific one that I might get to, but I want to open it up. So any questions for panelists as a group or individually, please make yourself visible and we'll have microphones. Yeah, is that the idea? Microphones make their way to you.
Hayden, can I make a comment?
Yeah, sure. Yeah.
So it's interesting because sometimes we don't realize for the last 2 years, I'm talking about dairy, this country export more semen than what we use in-house. So if we have a genetic evaluation for methane emissions, that will have a huge impact not only in US, but also in the rest of the world that is using actually the genetics that we produce here.
Assuming those phenotypes stack up and where they're going, right? I guess that's also the proven sire type thing. We have a question here in the center.
Yeah, this is a question for Francisco, and it has to do with the Canadian dairy evaluation for methane. I wonder if you could comment on their approach and whether that's something that could be replicated here or.
Yeah, I will be careful because I have a Canadian here on my right. So Canada implement a genetic evaluation for methane emissions a few months ago using indirect records of methane emissions based on the spectra instead of direct records. So what we plan to do is actually to develop a national genetic evaluation for methane emissions based on direct records of methane production. And we are also exploring the value of the spectra of the milk, but mostly for management. We strongly believe that we need a tool for farmers. So if tomorrow they need to mitigate methane emissions, they need to identify who are the cows that are emitting more in the farm. And if we have this prediction equation, then they will identify the farms and probably assign to some specific feed additives, for example, if they need to mitigate.
Francisco, would that management include the culling decisions also? Or just the management of the animals on the farm?
No, so we are planning to predict methane production in grams per day based on the spectra of the data. So when the farmer tests the milk, it's getting protein, fat, lactose, somatic cell score, and also value of methane emission for that cow. And that will have a huge impact on terms of management. It's also bring information if you think about a genetic evaluation, but it's mostly for management.
Okay. Any other questions? And Ash, yeah.
Thank you all for your presentations. This kind of crosses over both the nutrition, the genetics, and what Hayden just said about the Global South. Is there a relation, if you walk around a farm in Africa or in India or places like that, you can have very different feed compositions than what we have here in North America or down in New Zealand or Australia. What do we know about that crossover between the genetics and the pastures and how that kind of links back into the system?
I can, yes.
Well, anyone.
So that's a great question. We are working on that. It's what we call genotype by diet interaction. So imagine you run one of our trials with 64 cows, and we have a diet high in corn. So we run this trial for 7-8 weeks, and then at the end of the trial, we rank the cows in terms of who is producing more, who is producing less, right? We stop that trial and we change the cows to a diet high in forage. And we run it again for 7-8 weeks. If when we rank the cows in the new diet, there is a re-ranking, is what we call genotype by diet interaction. We do not know if that exists. Probably it does with extreme diets. So when we basically run a national evaluation, we run it for, let's say, the average condition. That will be the average diet, and we assume there are no interactions. But your question is, it's very cool, and we don't know the answer yet.
Yeah, and if I can add just a little bit from the beef perspective too, that gets even more important when we think about when we test these animals. So are we just testing yearling bulls and replacement heifers on a concentrate diet? And then if there is that genotype by environment interaction, they're going to spend, these cows going to spend the next 10, 11, 12 years of their life on a no intervention forage based system, and there could be loads of re-ranking that we just don't have a handle on. So that's going to have some pretty big implications for us in how we test and think about testing animals. Are we going to have to feed hay in sort of a trial based situation to get these phenotypes, or is that concentrate based phenotype that we would gather in a feedlot setting for those future breeding animals sufficient? So that's a huge outstanding question for us.
Thank you. And yep, please.
The slide that was showing energy uses, just want to make sure I didn't misread that. I think it say 4.9% attributable to methane. Did I read that slide right? That's a lower number than I hear bandied about. Much lower. Did I misunderstand?
Methane energy. Sorry, the methane energy. Yeah. So that's on our data set, which is primarily about 500 observations of Jersey cows fed diets that are common in North America and Nebraska. But yeah, I tend to think it's around 5%. I know I hear people trying to stretch it to 10 or 12%. I don't see it in a conventional dairy operation.
And we have a question in the back, and then Spencer here.
How do you deal with the confounding effects of management on your phenotype evaluations? The Italian research that was done about 10 years ago showed a common feeding center for 50 different herds and showed a variance in production of plus or minus 40%. And so I'm kind of confused working with producers every day of how we quantify that, knowing it has a huge impact on the outcome of those animals.
Who wants to?
Yeah, so that's a very good question. So at the end of the day, what we do is we define what we call a cohort group. It's like a blocking factor that actually you have cows that are at the same time in the same place receiving exactly the same diet, exactly the same conditions, and you include that in the model. So you basically, at the end of the day, you rank cows within that cohort group, let's say. And that, in that way, you control for the variability explained by the research farm, the diet, and in the season where you run the trial. If that was my question. Gotcha. So that was exactly the question of Ash, and I agree with you. I mean, we need to know the potential genotype by diet interaction. And if you change the word diet by feed additive, this is another question. What's the interaction between the genotype and a feed additive, right? We assume that it's an additive effect, but we don't know. So to your question, we don't know that answer. We are running trials right now to have an idea of what is the re-ranking that we observe when we change dramatically the diets.
Okay, another question. Spencer here. Oh, is there another one there? Okay, and then Spencer here, and then Sarah. Yeah. And that might be it. We'll see how we go.
First of all, I really appreciate the presentations, and my question could apply to anybody, and I'm picking up from you actually. I work in the Global South and in Sub-Asia, East Africa, and West Africa. We don't have the large herds, but we have a tremendous amount of conflict for scarcity of natural resources between pastoralists and pastoralists, pastoralists and growers, and growers and growers. So again, I don't expect an immediate answer, but in this broad range of topics you're talking about, do you think if you follow the road, is there any ending to this that might turn into a better use of natural resources? In other words, feed is a real issue. Cows right now in, I don't know, northern Kenya are going for about $1.50 a head. They can't keep them fed. And I'm just wondering if any of this work is eventually going to lead down that road.
Well, I can't answer your question, but it reminded me about feed efficiency. So, feed efficiency is something that we don't pay enough attention. Michigan State had this big project some years ago that I don't really know where the results are and how it's used. But, the geneticists should definitely look at feed efficiency and how that relates to methane. I think it may actually be a better selection criteria for reducing methane than directly selecting for methane phenotype. Sorry.
Spencer, and then just here, just here.
Hello, great panel. Just pretty impressive the amount of phenotyping that everybody's been doing. I'm just curious if you could elaborate a little bit, any of you, on the type of microbiome analysis that you all may be conducting. Is it amplicon-based? Is it genome resolved? And kind of what are some of the outcomes you're looking for there with that data?
Yeah, I'll talk really briefly, and I'm so far from a rumen microbiologist, I probably shouldn't even speak, but we're doing a combination of amplicon-based. It's sort of been the workhorse for microbiome for a long time, but shifting more towards whole genome shotgun sequencing and assembling those metagenomes. So I think that there's a lot that gets lost between microbial composition, right? You can find composition, but composition doesn't equal function. So we're very interested in have some ongoing collaborations that are trying to really drill into microbe function that's enabled by making those metagenome assembled genomes. And again, population level surveys and trying to tie that function back rather than just a similarity of microbiomes or a single taxa that looks like it's up or down regulated in this certain high or low methane emitting group, right? So trying to tie function back towards that continuous phenotype.
Any other reactions?
So in data we are tubing, we are sampling the rumen of extreme cows, and we plan to do either Oxford, Nanopore, or PacBio. So we will do long read sequencing at the rumen of the rumen. In fecal samples, we are doing 16S, but we are also targeting specific methanogens using ddPCR, so absolute quantification, to try to develop non-invasive traits that we can use.
Okay, one more question and then we'll, two more questions? Hosts.
Hello. Okay. Thank you all for being here. This has been a really fun panel. I'm wondering about the win-wins. So when you're selecting, you're looking at low methane cattle. Have you found any connections like, the same cattle that have, quote, low methane or lower producing methane, either on an absolute or intensity side, they also have better milk fat or better yield, or they have better feed conversion, and so that can maybe possibly translate for an ROI for a producer. Are there any of those win-wins that are, I mean, just that gentleman's question with like feed conversion, that's really important. Have we been able to track that, see that, or is methane in the little hub over here, or is it actually translating to positive production traits?
I can try to answer that. There is no free lunch, they say in this country. So our data shows that more milk production, more methane production. Well, it makes sense, right? Because cows that tend to produce more milk, they tend to eat more, they will produce more methane. So probably methane production, and Alex said, is not the trait that we need to target. We need to target a trait that somehow would adjust for milk production and metabolic body weight. So for example, if I'm in front of two cows, they produce exactly the same amount of milk, they have the same body weight, but one is emitting less methane than another one, I want that one. Or for example, if I'm in front of two cows, they are eating exactly the same amount of feed, but one is emitting less methane, I prefer that one. So you basically adjust methane production and you use what we call a residual methane trait. Now, the good news is our preliminary data is showing that more feed-efficient cows tend to produce less methane. And that is the win-win, because we have been selecting directly for feed efficiency starting 4 years ago. It seems we are moving methane emissions toward the direction that we want, and if we now select directly for methane, we will go faster, but those traits, they are helping us, the two sustainable traits that we will have in our breeding goal, right? Feed efficiency and methane emissions.
Thank you. I was going to draw it to a close, but one of the hosts of the summit wants to ask a question, so I'm in a difficult position. So let's find a mic for Charles, and I bear no responsibility for going over time.
It's your fault, Charles.
Sorry, Dr. Hristov, you kind of asked why you were on this panel. One question I wanted to clarify for this, and you mentioned it during your talk, but I think it might have glossed over a little bit. It was talked about the genotype and feed interactions, and then briefly the feeds and feed additive interaction. But you've done some of the only work on genotype and feed additive interactions that I've seen anywhere. And you've mentioned a no interaction based on that early data. Can you clarify that in layman's terms, what that would mean for?
Well, it simply means that low or high phenotype, methane phenotype cows reacted the same to the additives that we use. It wasn't just an inhibitor, seaweed, and several different additives. I have to say again, it's a small data set, but based on this, doesn't seem to be there is an interaction there with feed additives. More work needs to be done to actually have an answer to this question. Yeah.
But I guess the good news is it's additive to some degree. If you have low methane animals, you have additional opportunities through an additive. So it's good news, even if you're not happy about it.
Well, the good news would be if if additives or the diet of course will have an effect. But if additives can add an additional value to selection process, for example, but at least in our data that's not showing up.
Right. Okay. Right. Well, please join me in thanking the panelists. It's been really interesting.